tonight we have invited Martin Nielsen, Professor Martin Nielsen, for this cafe. He's from Denmark. He will introduce himself, I think, a bit in his presentation. Martin was one of the speakers, or one of the during the FIVE conference in this spring in Aarhus. And Martin is not only professor and working at the university, but he's also known in the Icelandic horse world. He was speaker during some world championships. Another question for you all, please turn off your cameras and turn off your microphones. Questions can be put in the chat. There we will have a look every now and then, and we will ask your questions. Have a great time, and Martin, the floor is yours.
Well, thank you.
Oh, sorry, I did something wrong.
All right, we'll try again. Can you hear me?
Yes,
hello.
I can hear you.
All right. I mean, somebody muted me. But yeah, thank you so much. Thank you for having me, and thank you all for tuning in tonight, or whatever the time is where you are. I, you know, didn't expect many people to be interested in this particular topic, so I really appreciate you taking the time. And no, I'm not going to be talking for 3 hours. Uh, I'm going to sort of give you an overview, talk about a few different topics, and give you some examples, and just give you some things to think about when you hear about a scientific study. I mean, it's really difficult, and it's not necessarily something you can just learn in just an hour or less. We have a whole PhD education that is pretty much about that. So, but I do appreciate questions, and I actually appreciate them during the presentation. I'd rather take them as we go through. If somebody sits with a burning question or just something that doesn't make sense that I said, please pop your question in the chat, and we'll try and address it as we go. And I see there's something in the chat right now. Yep, exactly. You can ask your questions in the chat. So, a little bit of a further introduction. I am an Icelandic horse person. I grew up with Icelandic horses. My whole family is very engaged and has always been with both breeding, training, competing, and organizing shows, such as big shows such as the World Championships and Nordic Championships, but also a lot of smaller shows. Um, and my mom ran a riding school for many, many, many years. It was also with Icelandic horses. So that's always been in my blood. I am, as the slide says, I'm now a professor at Aarhus University. I recently moved here from the United States, where I worked for over 13 years at University of Kentucky, that has an equine research center. During my time in the US, I also engaged in Icelandic horses over there. I was part of the association. I was actually on the board. I was the sport leader for a while, and also helped out announcing at some of their shows. So really had a good time over there. Some really good people in the States involved with Icelandic horses as well. Back here in Denmark since November, and everything is still kind of new. It takes some time to get used to a change of environment. Let's just put it that way. And there's just this society is just different, vastly from the U.S. So I am a scientist. I'm a veterinarian. I have all the degrees that you see there on the slide. My area of specialty is parasites and parasite control and diagnostics and things like that. I'm not going to talk about that tonight. That's a topic for a different cafe, perhaps, if you're interested. Very important topic, obviously. So today I'm going to talk about more generally about science, in addition to to doing my own science and research and working as a scientist, I've also been very engaged with the PhD education. So that's the education to become a scientist. I was a director of graduate studies at University of Kentucky. I've been mentoring many, many students and young scientists. So this is something that the topics I'll be talking about tonight are things that we do spend quite a bit of time on discussing and talking about. And you often hear in the public debate statements such as the one on the screen right now. Science has demonstrated, it has been shown, or it has been proven. And usually, whenever I see a statement like that, I know it's wrong because science doesn't do that. We don't prove things. And if we believe we have proven something, we're usually wrong. So that's just not how it works. So no, what does science do? I've been in this field for, I don't know, 30 years. I have still not proven a single damn thing. Sorry for my French here. Darn thing. It just doesn't happen. But still, I think I believe I have contributed to the knowledge, the body of knowledge and science in general, and I believe that I provided somewhat useful information. So we always say that a good study raises more new questions than it answers. So if you have a bunch of new questions after you've done a study or even just read a paper reporting a study, then it was a good study. That's how science works. And there's always more to learn. Sometimes we just find out that things are way more complicated than we want it to be, but that's just how it is. And we may just appreciate or at least acknowledge that complexity a little bit more. We also sometimes just realize that, we're pretty lost here. We really don't know much about this topic, and there's just a need for more work, more research. So, um, but still, we hear again in press and public media that a news article can provide a statement like this: a scientific study found that, a new study has just found that, and that is often true, not always, because sometimes the study is misinterpreted or overinterpreted, and I'm actually going to get back to that a little bit later. But but usually it is true that a scientific study can be described as having found something. It doesn't mean that it's the undisputed truth. It's just one study so every study has limitations, and one needs to understand what those are. And there's always more, like I just said, always more questions to respond. Only one study done in one particular location with one particular group of horses. Can you extrapolate to horses in general? What about different climates? I mean, it depends on what the topic is, but those are things that could be important. What about the age group? Are the young horses, foals, middle-aged horses, seniors, and then again, breed and lots of other things. So often what we do is, when a topic has been studied for many, many years, we and studied in many different parts of the world, people looking at maybe some of the same things, but studying them in different horse breeds, different horse establishments, different types of management, whatever it is, then you begin to look across the many, many different studies. And they're not all agreeing, right? They could, at face value, they could look like they're contradicting themselves, that there's this huge disagreement between studies done by so and so over here on one side and so over here on the other side. Yeah, that's how science also is. Um, but then when there's enough studies done, you can analyze across all the different studies, and that's where you're beginning to really get an idea of what might be going on. So today I'm going to talk about a few different things that are, common errors in scientific reporting, and these are errors that are actually done by scientists themselves repeatedly. As recent as this morning, I was reviewing a paper submitted to a highly respected journal, and it was full of these errors that I'm going to talk about today. I mean, consistently all the way through. I'm like, so anyway, so scientists make mistakes, and then the people reading the scientific papers and trying to report them in news media definitely also make those same mistakes. I'm going to talk about how do you actually reference a study? And then I'm going to talk about the strength of the evidence. So if you think of every scientific article as a piece of evidence, how big of a piece is it? How reliable is it? How strong is it? So we do have a little bit of a hierarchy that we can talk about there. And then, of course, and as the bonus at the very end of this talk, I'm going to give you a lecture on statistics. And I know you're all going to be looking forward to that. No, it's going to be very brief, but I'm just going to touch on a couple aspects of statistics that might be good to know and think about. So let's move on to how a scientific paper is written. So I'm a guy, and we guys in general, we like to put things in boxes. There is this YouTube video by a comedian that's called The Nothing Box. If you haven't seen it, search on YouTube and watch it. It's really funny. I mean, he talks about the differences between the male brain and the female brain. And, I'm not gonna I'm not gonna summarize that here, but the female brain, everything's connected. Everything is just connected back in time, forward in time. Things that happened 10 years ago has a connection to what's going on right now. Everything's very complicated. And in a guy's in a guy's brain, everything is neatly put into boxes. And when we discuss a topic, we go to the shelf, we find that box, we pull out the box, we open the box, we look at what's in the box, we talk about what's in the box, and when we're done, we put it back in the box, we close the box, and we put it back on the shelf, and the boxes don't touch each other. And then our favorite box is the nothing box. Now, if you're curious about what the nothing box is, go and look up that video. My point here in the context of a scientific paper is that this is how I actually teach my students to write a scientific paper. You just need to put things in the right boxes. And it's ironic that in this day and age, and certainly in veterinary science and also in my field of parasitology, almost all my students, graduate students, PhD students, master students, are female. They're all female. I mean, I've only had a single male student in my entire career. So, yeah. So I have to tell my all female students to think like a guy because that's the only way I can teach them. So anyway, so that's what I do. So so I define some boxes in a scientific paper, and let me just click that chat away. Okay, yeah. So and those boxes, as long as you focus on what needs to be in each box, you can write a paper and you can do it well. So the boxes are as follows. Introduction is the first section. Then there is a section called Materials and Methods where you describe what you did. Then you report the results. And then in the end, you have a discussion. Those are the four sections, and then you have references in the very end. So that's the fifth section. So as a subsection to the discussion, we also have conclusion. It doesn't necessarily have its own subheading, but the last paragraph of a paper has to be the conclusion of that study. So let's talk about what needs to be in each of these, and also what shouldn't be in each of these boxes, and then where you can go wrong when you reference a scientific paper. So the results and the conclusion are the two most important parts of the paper, and that's actually where you can and should reference. You can say the results in this study were that fill in the blank. And the authors of this study concluded that. So that would be correct. But then you really have to be careful if you find a statement in any of these other sections, whether or not that's actually something you can reference that paper for or not. So we'll see. So introduction, and I just pulled up one of my papers. So this is kind of how they all look. There's usually a summary or an abstract first, and then that first subheading is usually always introduction. So whatever is said in the introduction key is to provide the information that the reader needs to have in order to understand what the study was about and why it was a relevant and necessary study. So, the art is here to provide just enough information to make that clear without overdoing it, without writing a dissertation. And sometimes people write too long introductions, and we ask them to shorten them. And so it sets the stage for the study and then the paper, and these are some of the bullet points that needs to be talked about and summarized. And yes, you are going to reference other papers in this section. In this particular paper, all my references are highlighted in blue. That's just the style of this journal. But they're there, and then one can go and pull up those if they want to read more detail about whatever that statement was. So key here for the introduction is that nothing in here can be cited. Nothing can be referenced. Just because the first sentence on here that says equine cyathostomes, which are a type of parasite, are truly ubiquitous, means that they're everywhere, in grazing horses around the world. That's the opening statement. It doesn't mean that you can cite this paper for the fact that this type of parasite is everywhere, because this paper doesn't provide data backing that statement up. This is just an opening statement. So whatever's in the introduction, it cannot be cited, it cannot be referenced, and it is not scientifically shown or whatever you want to say. This is where people so often go wrong. And the paper I was reviewing this morning had done that repeatedly. So many papers they cited for things that the papers were not reporting, but might have mentioned in passing somewhere, typically in the introduction. So if you ever find yourself actually reading one of these papers, just understand that the introduction is just background information. It is not what this study was about. Well, maybe it is a little bit what it was about. It wasn't what it found, okay? So that was the introduction. Next section is materials and methods, second subheading, and that is where we describe how the study was done, what sort of material, where in the world were we, how many horses were included, what kinds of material, what kinds of samples, were they treated with something, did we do diagnostic test or whatever, all that. You can cite this section because it describes method. And next time somebody writes a paper, they may need a description of a specific method that they wanted to use. And if it's already described in another paper, you're better off just saying, well, I used the method of Nielsen et al. 2024, and put that reference in. Then you don't even have to explain what you did. Somebody can just go look up that paper. So that's appropriate as long as you only reference method in the method section. And there shouldn't be anything else in the section but method and materials, but sometimes there is, because people are really messy and they don't put things in the right boxes. So I have examples of people who provide more background information in this section. Now, all of a sudden, they feel an urge to explain why this method was the right method to use, and it's been shown by so-and-so it's a good method, and this is why we used it. Well, this is discussion, right? So no more background information, no discussion, and we don't want to hear about results in this section either. I mean, I see all these mistakes happening all the time, but that's just the structure of the paper. Doesn't necessarily make it a bad paper. It's just a messy read when people don't put things in the right boxes. So next section is results, again, and then usually key here is that whatever was described in the previous section, materials and methods, there has to be a corresponding result or a corresponding set of results. So if the materials and methods said, we collected these samples and we subjected them to this analysis and then we did this with them, then there has to be results of those efforts. Sometimes there isn't. Sometimes the results section brings results of something that wasn't described in the materials and methods. Sometimes materials and methods describes a methodology or procedure that for which there are no results. And so they have to match up, right? So very simple. I mean, you can all do a pretty good job reviewing these papers just by looking for these things without even knowing the subject, without even being trained scientists. It's not hard to figure out whether something was done, if it was described, are the results matching or corresponding to that method or and not? I mean, so that's it. Yes, you can reference results. It is very appropriate to reference results. You can look at this graph here in figure one and go, oh, they had two groups. The red and the blue were treated with something and they reduced their egg counts down to 0 at week 1, whereas the untreated control stayed, the green stayed positive. So you can say something like, this paper reported high efficacy of this treatment against this parasite and whatever you want to say, right? So yes, the factual information that's presented on the results can be referenced and it is appropriate to do so. So now we get to the discussion and you just see a couple of tables here from the results section. That's one way of presenting data, lots of numbers there. So in the discussion, this is the other section where people very, very often go wrong when they read a paper. And I say people, I mean scientists make these mistakes. So a discussion should discuss. That's a good discussion. We don't want to read more background information. That's not discussion. If you're referencing what other people found, that really doesn't belong in the discussion. That belongs in the introduction. But you should put your results in the context of what others have found, and that's a relevant thing to do. And then you can discuss why things were different or what new questions might have come around based on what you did, what knowledge gaps you now see, and what should be the directions for the future. Now, in a discussion, it is appropriate for scientists to speculate. That is absolutely appropriate. It is encouraged. It's also why the discussion is the most fun section to write, because you can sort of venture into your crazy ideas and suggestions. They have to be justified. You have to argue why you think that this is what is going on, but you're allowed to suggest, hypothesize, speculate, whatever you want to call it. That's a good discussion, should do this, right? This doesn't mean that it was shown or proven or demonstrated that these explanations may be the fact or not. So this is where people go wrong. They reference something that has been suggested as a possible explanation based on the results of this study and maybe some other studies, and that doesn't mean that it was demonstrated or shown or documented. And that's very, very important. And I also think in public news media and public discussion on social media, for that matter, that's often where people go wrong. This study said this. No, it's just a discussion. They're suggesting it. It could be this. We don't know, but this is maybe a path forward, something that should be pursued in future studies. So be really careful with that. You can reference a suggestion. You can say that Nielsen et al. Suggested that whatever it was, crazy idea. And that's appropriate. Or it was hypothesized that, or as long as you demonstrate that it is exactly that, a suggestion, not a demonstration. So then I said, look for the conclusions. Like I said, the last paragraph of the discussion, sometimes it has a subheading, and other times it doesn't. And a good discussion, a good conclusion should sort of go, all right, what did we learn? What can we say? And where do we go from here? The well-written ones do that, not all of them, unfortunately. So I'm going to pause there before I go into this next section, and let me see if there are any questions. Yes, so Eva is summarizing what I'm saying, so that's very good. Yes, exactly. So if you ever get exposed to reading a scientific paper or you hear about one that somebody is talking about, it's a good idea to go and just first thing is, so which box was this information actually in, right? Was it in the introduction? Well, no. I mean, maybe there's a reference, and then you should go look that reference up to see if they actually reported whatever that statement was. Sometimes they don't, because people reference papers for the wrong things, as I just said. But yeah, so look at where in that paper is that information actually. Is it in their conclusion? Is it in the materials? Sorry, is it in the results section? If it isn't, if it's something that's just mentioned in the introduction or in the discussion, well, one has to be really careful. Um, so yeah, scientific papers. There are good papers out there. There's also very bad papers that are still published and peer reviewed. It's not a perfect system. So just because something is published in a scientific journal doesn't mean that it is the undisputed truth. We could definitely still question it or ask questions about it, and we should. So that was that first section. As I mentioned in my introduction, I want to talk a little bit about the strength of the evidence, and so the hierarchy between different types of studies. And I'm not going to mention all the different kinds of papers and studies there are, but I'm going to bring you some examples of scientific papers with different uh, evidence strength, if you will. So at the very lowest part of the totem pole, we have the case report. Uh, Usually a one case of whatever it is, it was an example. Um, it's a single case of something potentially possibly interesting, a disease that wasn't described in that area before. Maybe a new treatment approach. Hey, we tried this surgery instead, and it actually worked well, and the patient survived or whatever. Um, and so that's good to know kind of information. Well, they found that in one horse. It could be good to know that this type of disease actually does occur in this area. We didn't think it did, but now there's a case. So, we should be aware of this. We don't know how big of a problem it is. We don't know how common it is. Is it just the one case of, will we never see it again? Or is it now the first of many? Do we have a pandemic rolling in? Right? We don't know that. So it's good to create some awareness, but in general, this has mostly local interest. It's interesting to whoever lives in that area, in that part of the world, in that country. In this case, in a municipality of Niagara, where so it's relevant to those people, and maybe not to the general international reading audience, or maybe it is, right? But it's only one case, it's a single horse, and there's only so much we can say based on that report. Now, there's also case series where people collect more than one of the same type of case. Sometimes they collect them across time, and then they try to sort of make an inference across the different cases and try to say, well, what's the general pattern here, what the typical presentation is, the general response to this treatment, and how many of them recovered completely, and whatever additional information you can get. Maybe, what does blood work look like? What kinds of diagnostic tests can you run? And now a case report is becoming much more valuable because it's now more than one horse, and therefore the evidence, the strength of the evidence has increased, right? So case reports are good. Sometimes that's where you discover something new, a new trend, or like I said, even the next pandemic for that matter. So another type of paper is a survey. And the typical type of survey is what we call a cross-sectional survey. That means that we go out at one time, one point in time, we go out to a horse farm, maybe a number of horse farms, and we collect information, maybe some samples from the horses. Then we write down how old they are, what breed they are, and whatever else we think is maybe relevant to know about, and that could have an influence of what it is that we're studying. And so we can't really control very much what types of horses that we encounter. Of course, we can do that a little bit in which farms we enroll, but once you get to the farm, we don't know what the age distribution is. It's definitely not going to be the same at every farm. Male versus females. Are there any stallions and all these things? A lot of yearlings and or not. And does the farm have foals or does it not? Is it not a breeding farm? And all these things we can't completely control, and especially not if we want to sample more than one farm. And usually we do because that increases the strength of the evidence, right? We don't have groupings. Usually it's just we go, we collect whatever is there, and we collect as much information as possible. And then we try to account for all of that in a statistical analysis, which is usually pretty complicated because we're going to look at many, many different factors that could all have an influence on the thing that we're measuring. So if we're measuring antibodies to a virus, and we're thinking about, okay, so what are the factors that could affect that antibody production? Of course, it's, have they been exposed to the virus, but it's also, how old they are, what time of year it is, have they gone to shows, or are they staying at home all the time, and are they suckling foals? They might have maternal antibodies through the milk from the mare, and there's all of these additional things that could also affect the antibody concentration in the blood sample. And so we try to account for that in the statistical analysis. Now, this is where one has to be really careful because, you do the statistics and then you sometimes find what we call a significant association, right? There is a statistical relationship between this thing and this thing. They're connected. So one really has to be careful because it doesn't mean that they necessarily are directly connected. It could just be how the data were collected. There might be an intervening variable that we didn't account for, but they're both relating to that, and maybe that's why. And also, we can't say whether one led to the other, or the other led to the one. Is it the egg or the chicken? We can't say. We can just say that they're connected somehow, but whether one caused the other or not, we don't know. And let me just give you an example of a study that I was involved with many years ago. A veterinarian in Denmark reached out to me and said, "Hey, Martin, I need to do a scientific study. For this continuing education degree, we all need to do a project, and I haven't had time to think about it much, but I need to do one. And I spent so much time at the racetrack, the standardbred trotting track here, and they all poop, so I could easily get fecal samples from them all. And my thought was, I could look at parasite egg counts in those fecal samples, and then we could try and correlate that to how they do in the race." And I said, that's not going to work. You're looking at one variable out of many, many, many potential things that could affect race performance and the chances of success. And you're not accounting for any of those other possible factors. I mean, there's the trainer, the feeding regimen, the how experienced the horse is, and how all these other things, breeding bloodlines, and you name it, right? And you're not accounting for any of that. You're just looking at a fecal egg count. And by the way, parasite fecal egg counts don't really correlate with the worm burden. So high egg count doesn't mean more worms than a low egg count. So we can't really use that for much. And most horses have some parasites, and so what? I mean, we can't say it necessarily affects performance. I gave him this long, long, long lecture, and he listened. And as I was finally done, he said, "All right, but I still want to do it. Will you help me?" And I'm like, "Okay, but did you hear what I said?" He said, "Yeah, yeah, yeah, I know, but I just need a project." And I don't care what the results are. I just need to have a project so I can get this degree. And I said, all right. And so we found a statistician. That's the guy in the middle author. And we tried to at least account for as many of these other factors as possible. It's still not an ideal setup, right? Just trying to relate race result with parasites in the fecal sample. It's really far-fetched. Now, what we found was, to our surprise, that the horses that were successful in the races, finishing in the top three or winning the highest amount of money, had higher parasite egg counts. And nobody expected that. And so that's a correlation. That's a statistical association with the parasite egg counts in the fecal sample and race performance. Does it mean that parasites make horses run faster? No, right? No, we can't conclude that because it's not a causal relationship. We can't say that A led to B or B led to A. Does running fast make horses have more parasite eggs? Right? That's also a difficult one to explain. It actually made the discussion in this paper kind of fun, kind of interesting because we could really speculate. So we came up with some wild theories, and I'm happy to share the paper if somebody's curious and wanting to read it. So just an example, we found an association, but why that was there in this study, we can't really say. Just interesting. But certainly, parasites, we can't say that the parasites made the horses run faster, but we can also say that it certainly didn't affect the performance negatively to have the parasites. So maybe that was the take-home conclusion from this study. So another type of study that is stronger than the cross-sectional survey is any kind of longitudinal study where you go back and sample the same horses again and again across time because you get more data points and you now can account for seasonality, which often affects the things that we're looking at. And so the more data points you have from the same horse, the stronger that study is. Now, sometimes you see a study presented as a longitudinal study where data were collected across time from horse populations, but where the data weren't necessarily collected from the same horses, but just from some horses, then it's really not a real longitudinal study. So one has to be careful there. So more statistical power, and then often in a longitudinal study, you're able to set up different groups. It could be different types of treatment, exposure to different types of whatever pasture or pasture management, whatever you're looking at, and then you can do a comparison. Um, so, so longitudinal studies, and they could be forward in time, but they could actually also be back in time retrospectively. That just requires that we have the data recorded already, and we sometimes do, but often we don't, right? If you weren't expecting to be doing a study, why would you be collecting data in a certain very systematic manner necessarily? So often we can't do it retrospectively, but you sometimes see this type of study reported from university hospitals where they can go back and look at their records of different cases that they have observed over time. So another type of study that is actually a strong study design is the case control study. And that's where you do have groups, usually two, sometimes you have more, but as the name implies, you have a case group and then a control group. And the case group could be horses diagnosed with a certain condition, certain disease, or whatever it is. And then key with the control group is to make that group as similar to the case group as possible, with the exception of that, whatever defines the case, the disease or the diagnosis or whatever it is. Like, so everything else would be the same. That would be ideal. So same age, same sex, if that is the case, the same breed, same time of year, um, and whatever other parameters you can come up with that would make them match. So we really want to match the two groups as much as possible. And of course, that's not always possible. Same farm. Um, I mean, there's only so many horses present in a farm. You can't always just pick and choose, right? So you have to compromise, but at least make an effort to match as many of these important factors as possible. And the better you do that, the stronger the study. And then a big important key here is that the group size in a case control study doesn't have to be very large. You don't need a huge number of horses for it to be a good study. And then sometimes people go wrong on just the number, how many horses were included. Oh, if there were like 100 horses, then it's a strong study. And if there were only six, then it's a really weak study. It's not really a study, it's just a student project or whatever, right? No, not necessarily. So I'll show you an example of this here in a little bit. The strongest kind of evidence scientifically in scientific papers is what we call a meta-analysis. And you may recall in the beginning, I talked about looking at trends across different papers, different studies, looking at the same thing, but being published and conducted in different parts of the world. Once you start, picking up trends in the big picture, that's what a meta-analysis does. So you kind of take it's a statistical analysis that you do across the data from many, 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 many studies, as many as possible. It could be lots and lots of data points. And then you ask, is there really a trend or is there not? And then you try to account for a lot of these other things. So a meta-analysis is, at least on paper, potentially the strongest kind of evidence you can find. If something is reported in a meta-analysis, it is stronger information, but not always, because there are bad meta-analysis out there. Oh gosh, I see a lot of these. One of the other jobs I have, I forgot to mention this in my introduction, is I also work as a scientific editor for one of these journals. I see a lot of papers every day. I look at papers that are submitted. And I see a lot of these meta-analyses, and gosh, there are some bad ones in between. They're bad often when there's just very little data out there to meta-analyze. If there aren't a lot of studies, it's pointless. And especially if you have very, very few studies and one or two really, really big studies with lots and lots of animals or whatever it is you're studying, and then a bunch of small ones with, just case studies or like 2 and 5 and 3. And because then those couple of studies with the many, many, many animals, horses, are the ones that are going to be driving the outcome of that meta-analysis. And then you didn't have to do the meta-analysis because you could just look at those two studies and look at what they found. And that's what the meta-analysis is going to conclude. And so there, of course, there's good and bad examples of any type of paper and study. And just because a paper says that this is a meta-analysis doesn't necessarily mean that it's a good one. But try and search the term meta-analysis, like the one down here, then you're going to find so many papers. It's been very popular to publish meta-analyses in recent years. I think it got a little bit too popular or easy for people to do, and some of them got away with publishing some not so good ones. So yeah, statistics, right? Let me see. Okay, I see a question. In meta studies, often also negative results are most often published, so there's a bias towards positive results. Yes, that's a general problem in science. When Machtel said negative results, it is what it really means is that you looked for a difference or an effect of something and you didn't find it, and you didn't have that statistical difference between your groups or whatever you're looking for. Then in many cases, people don't publish, or it doesn't get published even when they try to publish it, because At least many journals still today feel like, well, it's not really significant if they didn't find any difference. I mean, it was inconclusive, right? And then it's left out. And then so you don't see that as part of the data that's made available for that meta-analysis. And so then there can be a bias in some of these meta-analyses. That's absolutely correct. We have seen a trend in recent years towards um, accepting these types of papers that are reporting the so-called negative results of, just lack of statistical significance results in as long as people aren't over concluding and making the data, you know, making more of the data than the data actually allow, then that's actually perfectly appropriate. And I'm part of a paper that was accepted for publication this morning where no differences were found whatsoever, but it's still a paper that got accepted in a respected journal. So I think that trend is also changing. So let's see, there was another one. Oh, it's still Eva who's just summarizing what I'm saying. So that's awesome. So let's see. This is a question. Yeah. So how can it be made easier to look at the paper? Yeah, I wish I had an easy answer. I mean, so it is not easy. And um this is also the reason why people get away with sometimes getting something published that really shouldn't be published, or where just the conclusions and the interpretation of the data weren't supported by the study, and the paper should have been rewritten. And, and I think, uh, I mean, it's happening because it's difficult to make this assessment, and I also think that um, there are so many scientific journals out there that and not enough people to review the papers. That's still a voluntary task that we all take as much as we can, but we don't get any compensation for it. It's just something that we're all expected to do. And people are very, very busy. I can say as an editor, it's difficult to find um, qualified people to review the papers that I receive. It can take a long time. So there's lots and lots of weaknesses out there. Now, the counter to publishing in a scientific journal with peer review, as it's called, the counter to that is just to publish it as a preprint. So an open paper, put it out in the open without review. Just put it out there and let the readers make their own assessment and judgment. And there certainly are arguments for that and value in making a paper openly accessible to everyone where you don't have to subscribe to a specific journal to read it. And if you know the subject matter, you can tell for yourself whether you think it's solid work or not. Um, but it is, so I'm not saying that I'm not saying that the peer-reviewed model is a better model or this one is a worse model. I think bottom line is that you have to do your work well. And as a scientist, and I also still believe in the old-fashioned peer review model, and at least I see it as my job and responsibility to improve the paper that is presented to me as a reviewer. I'm always thinking, how can I, help improve the quality of this paper? What are the changes that I should ask the authors to make before we can accept this paper? So let me see. But make it easier to look at the paper. Yeah, I mean, people are also not always very good at writing them in a manner that make them easy to read. Sometimes I get the suspicion that it's almost deliberate that they make it difficult to read because, then people won't be able to criticize it as easily. I don't know. You make it sound more complicated than it is. You want your research to look complicated because it makes you look like a better researcher. I don't know, but sometimes I get that feeling. I mean, some people would be really upset with me now if they heard me say this, but sometimes it feels like there can be an element of making things look a little bit more advanced than it has to be. I mean, you really just have to explain what you did in an easy manner. And it's always been my approach. Um, overconcluding is also a real problem. That is absolutely the case. I agree with that. Um, and not everyone has access to these journals. That is true. PubMed is openly, that's a search engine that's openly accessible to everyone, as is Google Scholar, where you can search and you can find some of the papers, but they're not all open access, and that's a whole different topic altogether. Open access is journals where I, as the author, actually pay for getting my paper published, and sometimes a hefty, substantial fee like three, four, $5,000 to get my paper published, and then it's open to everyone in the world without a paywall, and that's sort of neat. We like to make our information as widely available as possible. I still think that there's something fundamentally wrong with me doing all the work to get the paper done and the research done, and then I have to pay a journal to put it on a website. I mean, come on. But anyway, that's maybe on the side. So you have access to the search engines, and you can read abstracts from all the papers, but you can't necessarily read all the papers in full. But some of them you can, right? And then there's always a corresponding author listed with the paper, and then you can email them and ask for a PDF of the paper. And if they're nice, they're going to give it to you. I mean, I always do that. So there are ways to get a hold of a given paper. All right. But you're not going to avoid the statistics. So I am going to talk about it, right? You can ask as many questions as you want, but I'm still going to spend a few minutes talking about some of the aspects of statistics. And don't worry, I'm not going to get deeply into this. In scientific studies, we often talk about a power analysis. Many papers would actually describe this as part of their materials and methods, that they did a power analysis to find out how many animals they needed to answer the questions that they were asking. And that's the statistical power we talk about here. So how many animals are necessary? And depending on what we're exposing these animals to, so maybe we're drawing blood samples, so we're injecting needles into their veins, or we're subjecting them to the stress of rectal examination or whatever it is. We can't just, there's animal ethics here, so we have to also keep that number at the absolute minimum and not go much, much above that just because we think that's better. So, so in order to calculate the power, we need to know the data. We need to know the type of data that we're going to record. And especially when we need to know how much variation there typically is when you do this type of measurement. Is it something that really varies and jumps up and down a lot, or is it something that really doesn't vary very much? That largely determines your power, because if it's very variable, you need more animals in order to detect a difference between two groups with any statistical certainty. And we talk about two things that we measure or we determine in a power analysis. And one is the effect size. So how big of a difference between two groups are we interested in determining, right? It's not all differences that are relevant. Like, there can be so small differences that they're not biologically meaningful, and then therefore also not meaningful to set up a study, to design a study to detect an effect size that's this small, right? So what is a meaningful biological difference effect size between our groups that we want to determine? So that's one thing we have to decide, and we have to justify that. It could be a difference between a treated group and an untreated group or something. It can be a vaccination effect or a comparison of two different vaccines or whatever it is. And then the analysis will tell us how many animals do we need in order to do this. And the larger the effect size is, the smaller the group size is, and vice versa. So, power analysis. And one example of that is a topic that was hotly, pun intended, hotly debated about 15 years ago in Denmark. And you may have had, I don't know, you've had similar discussions in other countries. I'm sure you did. Danish warm blood horses and also some other warm blooded horse breeds had a tradition of hot iron branding, um, and had had it for many, many years. Um, and the discussion was whether this was justifiable. Was it animal ethically justifiable, and was it how painful was it to the horses? And so a study was done by some colleagues of mine at the University of Copenhagen. I wasn't involved with this at all, but I was there at the time, so I also overheard a lot of the talk and discussion. So this paper found that horses actually showed signs of pain reaction to this procedure. And some of you may be thinking, well, of course, come on. Why do we need a study to determine this? Anyone can logically um, just conclude that, of course, this is going to be painful, right? But that's sometimes how science also is or has to be, because if there are financial interests in something, it can be a difficult discussion to have without strong evidence that definitely demonstrates that this is the case. So this paper did so. And that initiated a long discussion. Um, One of the criticisms was the group size, only 7 horses. So the Danish warmblood and people associated with that association, that was their argument. This is just a small study. It was just a student project. It wasn't real research, and they only looked at 7 horses. We can't really use this for anything, and it shouldn't guide our policies within the association. So um, they actually found another study that also had evaluated pain reactions to hot iron branding, and that study had more than 100 horses. So their argument was, that study with the more than 100 horses really concluded that reactions were minimal, horses were fine, there weren't really any issues, very few of them reacted, and they all recovered and were fine, right? And so, at face value, a study with more than 100 horses versus a study with only 7. I mean, our friends at the University of Copenhagen, it doesn't look good for them right now. It looks like the people at Danish Warmblood found a stronger study that was a counter argument. Now, one has to look into the specifics of these studies. So the 7 horses were divided into 2 groups. Actually, it was a crossover study. So they compared the pain reactions to microchipping as the alternative. So, and it was a crossover. So first, 3 of the horses got the microchip, and then the 4 of them got the hot iron brand, and then they recorded all the pain reactions to that. And then they waited for I don't know how many weeks for the brand to heal and the horses to recover, and then they switched group. So the horses that were originally hot iron banded were now microchipped, and vice versa. So yeah, 2 groups, but all 7 horses were exposed to both treatments, if you will. So that increased the strength, and they compared to microchipping. And then the study was conducted by people employed by the University of Copenhagen that had no involvement with any breeding association, any interests whatsoever. So, and they were able to find a statistical difference in the different pain manifestations between hot iron branding and microchipping, much less reaction to the microchipping. The 100 horse one had no groups. There were no comparisons. They were all hot iron branded. So nothing to compare to. There were really only observations. A guy was looking at the horses and concluding that they were fine. There were no measurements, no objective measures of pain manifestations. And by the way, he was an employee of the organization, the breeding organization. I think this was Switzerland or Austria or something like that. So highly biased study. So now with all this information, we can ask again, so which of these 2 studies provided the strongest evidence? It was the 7 horse one because of the tight study design and the objective measures. And you can involve many horses as possible in a study, but if it's a poor study design, it doesn't make it a better study. So I'm going to end with a few slides here on when a difference is a difference. And that's really where we use statistics. So, very complicated graph here. We have two data points on a graph. We have group A and group B. Group A has a measure of about 100. Group B is about 65 or 60 or so. You know, at face value, it looks like group A has a higher number than B, right? So, there's a difference between the groups. So, is there really a difference between the groups? This is where we need a measure of the variation between the data points. We can't just look at an average or a mean or a median. We need to have some kind of measure, and there are different types of how much variability is there between within each of these groups. So usually in a graph, we mark them like this. We call these error bars. And you can see that they sort of represent a range of data points or an interval of data points of some sort. And like I said, there are different types. But these two groups now have these ranges on there. And what we notice now is that they actually overlap quite a bit, actually by almost 50%. So 50% of the data points with group B actually overlap with 50% of the data points in group A. And so, most statistical analyses would not find a real difference between these two groups. They're just two numbers that one looks a little bit higher than the other, but really these groups are not statistically different. And then we can ask, okay, so what was the power here? What was the power analysis? What was the group size? And all those questions. We can look into that. Now, maybe we have a different study with a different measure or whatever it is that is less variable. And so our error bars now look like this, very tight, beautiful, one would say. And one thing we notice is that now they actually don't overlap. And if we do a statistical analysis here, very, very likely we will find that group A had statistically higher values than group B. And we can conclude that they were significantly different. Whatever group A was exposed to or represented or whatever happened in group A might be associated with this higher value. So the variation is important when you look at data and data points, and that's what statistics actually helps us with. Well, when done well and appropriately. So that's all I'm gonna bore you with tonight. I'm happy to take more questions if you have any. A little anecdote about the horses in the picture, by the way. These are research horses that I had available at the University of Kentucky when I worked there for the 13 years. And interestingly, this particular herd of horses had not been dewormed since 1979. So when I left, 45 years of no deworming, and they have lots and lots and lots of parasites, really all the parasites you can imagine, and in high numbers, and are remarkably healthy horses. So great fun to have those and work with them for so many years.
And if there are any questions, you can still leave them in the chat, and we'll wait. Yeah.
Thank you, Belinda.
Martin, do you have something where people, if they have questions afterwards, where they can contact you?
Yeah. Actually, I was just thinking of that. Let me see if I can find my page at the university that has my contact information and all. Yep, this is it. Oh, copy. So that
Yeah.
has my email address and a little bit of information about me and the work that I've done.
Okay. Thank
Yeah,
you. So if there are any more questions, you can still leave them in the chat, and otherwise, we will. You can contact Martin. Um, Martin, for now, I don't have any questions. I don't know, Marcia or Marina, do you have any questions as co-hosts of our cafe?
No, I would like to thank you as well, Martin. It was very clear and no questions for me.
thank you.
Well, the only question that I do have is how can we, I hope you are okay with that we make this available to everybody in the NSFA, because I think it is
Sure.
very kind of basic information that you can really use to figure out if what is ever published or presented or challenged on Facebook or whatever,
Yeah.
how you can make your own opinion about it, because there's so many sometimes very contradictory results or opinions, and how do
Wow.
we
All
find
the
our
time.
way into that?
Yeah. Yeah. No, science isn't clear cut and often there are agendas sometimes also behind studies, right? And I guess we're all subject to bias, even in our own reporting, and no one can really just claim to be completely unbiased. But certainly, certain studies supported by and written by people working for certain companies and things like that. I mean, yeah, you have to take things with a grain of salt and try to look for the strength of the evidence. Yeah.
Yeah.
Maybe that's a good take-home message as well. Not only look at the box, but as I did my study in humans, it's also very good to look at who is financing the
Yeah.
study. So, and with what kind of glasses are they finances? Are they giving the finance for the study? Yeah.
Yep.
That's
Yeah,
also
no,
an issue.
that's a good point. Thank you for bringing it up. Yeah, no, that was also kind of part of my point with that story about the hot iron branding in the end, right? And look at who who reported it and where they're employed, right? Who pays
Yeah.
their salary? Yeah,
Yeah.
yeah.
And personally, I'm very curious about, did you publish any um, papers about your Kentucky study group of horses? Because
Yes,
it's very interesting to see what
yeah,
happens to I mean, it's very intriguing that horses with lots of parasites can still be very healthy. So
yeah.
have you
No,
published?
we published quite a few studies on this herd. Yeah, it was very interesting. Yeah, I mean, so parasites can cause disease, obviously, but they don't always do that. And even
No.
sometimes horses can run quite fast with parasites,
Yeah.
as we learned tonight.
Yeah.
And yeah, so we're changing subject here, but like I said, I'm happy to come back and talk about parasites another time if you're interested.
Oh, yes.
But it's a it's a it's a it's a normal state for horses to have parasites in their intestinal tract, and we can't eradicate them. And we've tried that for too long, and we've only gotten a lot of drug-resistant parasites out of it. So
Yeah.
just like there are bacteria in the gut, I mean, there's also parasites, and it's normal, right? So we need to better understand what are the conditions that might then sometimes lead to disease with parasite involvement, and that's again a more complicated question, but one that I work on. So.
Not very easy to put that in a very good scientific template, so to say.
Yeah, right,
Yeah,
exactly.
yeah. So
Yeah,
many. Yeah.
Or in a very interesting evening
Yes.
with a good story.
yeah,
Yeah.
Yeah.
Well,
Well, okay. I think we are closing the cafe. There aren't any further questions. So again, thank you very much, Martin. And I think we'll come back to you for another evening.
yeah.
definitely.
Anytime.
We'll
Thank you
be
very much
yeah.
for a very clear and understandable, and also, I think for a lot of people, enlightening idea about or lecture about how to look at studies, because it's not such an easy business.
It's not.
Great.
No.
Yeah.
Okay, thank you.
Thank you. Thanks
Thank
for
you.
having me.
We'll have contact.
Yeah. Yep. You know where to find me. So
We'll stay in contact.
Yeah.
Yeah. Everybody, thank you very much for being here tonight. And there will be link later in a few weeks' time for the recap. And if you have any ideas for other evenings for the cafe, just let us know. And thank you for participating all. Good evening.
Bye bye.